We're going to wrap up 3.2 today with a little derivative rule of the absolute value function, but just before I do that, I want to go back to this number 2 that we ended with last time, and I want us to add one more part to it because I keep saying that you're going to have to do more simplifying, and it's situations like this. So let's take a look at this example. It's definitely something that you could be asked to do in this chapter as well. So if I was asked for what x does f of x have a tangent with a slope, a tangent line with a slope of 1/4, then this is, we've done a lot of these questions. Most of the time I think I've done a lot of like where are there horizontal tangent lines. So a lot of those we're setting the slope equal to 0 or the derivative equal to 0. So in this situation, you know, what we're trying to think about is we're looking for where. So if we think about the work we need to do is we need to figure out where the slope of the tangent line is equal to 1/4, and that of course means we're looking for where the derivative is 1/4. So these kinds of questions require us to set the derivative equal to some value and then solve. So if I was looking at my derivative, which is 2 over, and it's up to you. If you like the 3/2 and working with the rational exponents, that's fine. Sometimes it might be useful. Sometimes people prefer to look at those in their radical form. So let's say the square root of x squared plus 2 with that quantity cubed on the outside. If I put it on the inside, I definitely need parentheses around the x squared plus 2. But I'm looking for where that's going to be 1/4. So a quick way to kind of solve this one, of course we need to clear the fractions. A decent visualization of this is actually the cross multiplying idea. I say it quietly, like I don't want someone to hear me, because a lot of times math teachers, a lot of us hate cross multiplying, myself included. But in the interest of space, that might be the best choice here. I'm a little short on some room, but I'm going to create some room here. I'm going to erase that. And give myself just a little extra space here. So this was equal to, I'm looking for where this slope is 1/4. So what is cross multiplying really? You're just clearing the denominators. That's all you're doing. So you're just multiplying both sides by both of those denominators. That's all that cross multiplying really amounts to. It's just that after we make this observation, it can be a quick way to kind of get there in our heads with the mental work. So we reduce the 4's here, we reduce the radicals there, and so what do we really have at this point then? All right, we would have had 8 on the left, the 2 times 4, and then on the right-hand side, we just have the radical, the x squared plus 2 square root quantity cubed. All right, and again, I'm going to solve this. I could have left it as the 3/2 power. I'm going to kind of do this in 2 steps. So to get rid of a cube, you take the cube root, or I'm even just going to write this in the interest of just room here, and I don't like the look of a root over a root. I'm raising both sides to the 1/3 power to first get rid of the 3. Now, in evaluating 8 to the 1/3 power, you really do need to think of that as a cube root of 8, which is 2. Keep in mind, if I was taking a 1/2 power or a 1/4 power, anytime you take an even root, like this is a cube root, so we don't need a plus or minus. If you take a square root or a 4th root, then you need the plus or minus. Here I don't, because I was taking a cube root. And so then what I have is just the square root of x squared plus 2, because 3 times 1/3, powers to powers we multiply, so that's just to the first. And now, in order to get rid of the square root, we can square both sides. And so we now have 4 on the left equals our x squared plus 2. And so we're nearly there. Of course, now we can just subtract the 2. And so we're at the point where we have our x squared equals 2. And so our last step here is, and here's the point, if you're taking a square root or a 4th root, then that's where we have to remember to introduce the plus or minus square root on the other side. So we end up with plus and minus the square root of 2. So we have 2 locations, and I'm just going to stop with the x locations. If we wanted the y locations, we'd have to sub those back into the original function. But let's also take a quick look at our graphing calculator on that, and just kind of take a quick peek here. So I've already taken the liberty of entering in the original function in my y1, x over the square root of x squared plus 2. And, just maybe go to a zoom standard window. That's the zoom 6. And now as you kind of look at your function, if you wanted to verify this and look at the value of the derivative at square root of 2 and make sure it's 1/4, we can do that by doing the second trace. So we're going into the calculate menu, and it's number 6 is the dy dx, or the derivative, so number 6. And then you just enter in the value, so the square root of 2, and hit enter. Again, these are the same commands on your calculator, though your display on the graph is a bit different. But what I want you to notice is on the last row under the graph, it says dy dx, and on the right it says y1. I don't love that. But dy dx is equal to 0.25, and that's the 1/4. If I did this again, the second trace, the calculate menu, number 6, dy dx, and I did it for negative square root of 2, because those are my two answers, again, I am getting this 1/4 value. So here's just kind of an opportunity for us to take a look at actually looking at something on our graphing calculator there. All right, so now let's get into the absolute value rule. So this is one that we can again talk about it in this section because of implicit differentiation being used in its derivation or its proof. So we are looking at taking the derivative with respect to x of the absolute value of x. Now, what we need to recall is that technically, when we think about the square root of x squared, where x takes on any values positive or negative. If I said to you square root of 3 squared, yeah, that's just going to be root 9 if you wanted to do the work, and it's 3. But that's the exact same thing you get if you do the square root of negative 3 squared. That's also root 9, which is 3. So technically the square root of x squared isn't x. If x can take on positive or negative any values, then it is the absolute value of x. Like the square root of that negative 3 squared came out to be the absolute value of negative 3. So that's what we need to recall here. And so as we think about that, so let's recall that. So now what am I really doing here? All right, so I am now looking at this as taking the derivative with respect to x of exactly what I said in my little recall down there. We're going to think of this as the square root of x squared. And now I want us to think of this as being, so the derivative with respect to x, I want you to think of this as an inside function, so let's call this x squared, being inside of this outer square root function, and we're going to think of that as our 1/2 power. So again, we don't just want to make that x because it's technically the absolute value of x. All right, so we're taking this derivative and we are going to apply chain rule. So by chain rule, we are going to say that that is going to equal 1/2, and we're going to say inside left alone here. So 1/2 inside left alone, now to the negative 1/2 power, and then by chain rule times the derivative of the inside, so times that 2x. So my 2's are going to reduce, and I'm now going to have in that first term here, I'm now going to have this quantity to the negative 1/2 can move into the denominator where it would be to the positive 1/2. So if I do that, I would now have my 1 over x squared to the positive 1/2. And then of course this is still times this x, which will slide up in the numerator. And this x squared to the 1/2, that square root of x squared, that is our absolute value of x. So if you go back to the original form, that is our absolute value of x, and then times that x in the numerator. So this becomes x, x divided by the absolute value of x. Now, in conjunction with chain rule, of course, anytime we learn a new rule, we have to think about what it would look like with chain rule. So with chain rule, the derivative of the absolute value of, if you have some sort of function of x on the inside of that. So let's say this is some sort of, I did not give myself much room there, hold on. Some sort of inside function, so something more than just a plain old x on the inside. So the derivative of the absolute value of a function of x. So the derivative of the outside is the absolute value rule we just looked at. And so that's going to be x over the absolute value of x. But the x, if you will, the inside, is left alone. So it would be f of x over the absolute value of f of x, and then times the derivative of that inside with the conjunction of chain, in conjunction with chain rule. So that's what it would look like with chain rule. So now we have that in place here. And I think I said the reason that when I started this, is that we use implicit differentiation to prove we don't. So why did they wait until this section? Because it was the rational exponents, which were proved with implicit differentiation. So that's why this rule comes up in this section. We needed rational exponents, and that was proved with implicit. All right, so we're not going to do a whole heck of a lot with this. I'm just going to take a look at one quick example. And in this one, again, we're just going to find the derivative. And so I've actually went through and we've shown what this derivative rule is. In your homework, they may like recreate this every time that they go through this process. We don't really need to because we've already shown it once, and that's enough. All right, so let's look at our finding the derivative of the absolute value of cotangent of 2x. So again, this is going to be the chain rule form of this. We have the absolute value of a function of x. So by our chain rule form in the upper right-hand corner up there, that means our dy dx is going to equal. So the derivative of the absolute value function is going to be whatever's on the inside, that function left alone, so cotan of 2x, and then divided by the absolute value of that inside function left alone, so that's our derivative of the outside, and then times the derivative of the inside. Well, the derivative of cotangent of, and now if I think about my inside function of that, so the inside of cotan of 2x, so this requires its own little chain rule. So the derivative of cotangent is the opposite of cosecant squared of, again, that inside function left alone, and then times the derivative of its inside, so that would be times 2. So this whole thing right here, that really represents the f prime, the derivative of the inside. All right, so that's our derivative, and I'm just going to kind of leave it like that. I mean, maybe I just clean it up and say negative 2 cotangent of 2x cosecant squared of 2x, all divided by absolute value of cotan of 2x. I mean, we could maybe clean that up a little bit. Cotangent's cosine over sine, and cosecant squared is 1 over sine, so we could maybe combine some of those. I don't know if it would really look a whole lot better than this, so we're just going to leave it just like that.